Hello everyone, welcome to Module 5, Work and Energy. So in this lecture, we're going to talk about work, energy, conservation of energy and power. So let's start with section 1, work. So the objectives here are to recognize the difference between the scientific and the ordinary definitions of work, define the work by relating it to force and displacement, third, to identify where work is being performed in a variety of situations, and fourth, to calculate the net work done when many forces are applied on an object. So let's start with the definition of work. So work is generally done on an object provided that a force generally causes a displacement of the object. So when you have a force and it causes a displacement, we only say then that the work is done. So work is done only when components of force are parallel to the displacement, to a displacement. So if you have an angle between the displacement and the force, so it's generally given by W equal to FD cos theta. So if cos theta equal to 0 degrees, so W is equal to FD. But if this theta is 90 degrees, W is 0. So this is called as the maximum condition and the minimum condition for work. So let's start with the common sense. So that is work. Let's get into the section 2, energy. So the objectives here are to identify several forms of energy, calculate kinetic energy, apply the work kinetic energy theorem, distinguish between kinetic and potential energy, and classify different types of potential energy. Finally, to calculate the potential energy associated with an object's position. So let's start with kinetic energy. So the energy of an object due to its motion is generally called kinetic energy. And kinetic energy depends on two main quantities, speed and mass. So it's generally given as Ke equals half mv square. So where m is mass and v is the speed. Now, let's talk about the work kinetic energy theorem. So what does the work kinetic energy theorem say? It says that the net work done by all forces acting on an object is equal to the change in the object's kinetic energy. So the net work done is change in kinetic energy. Now, this net work done is change in kinetic energy, so which is basically the final kinetic energy minus the initial kinetic energy. So let's take an example of a nail being hit by a hammer into a wooden wall. So let's consider the net force here. So the mass here is the mass of the hammer that is being pounded here, and the velocity is the final velocity square minus the initial velocity square. Now notice that the final velocity is generally going to be 0 because the hammer will eventually come to a stop, so which means that the net work done here is negative half m of the hammer times vi square, which is the initial velocity square. So let's take an example and let's try to use an example to solve this problem. So what is given here? On a frozen pond, a person kicks a 10 kilogram sled giving an initial speed of 2.2 meter per second. How far does the sled move if the coefficient of kinetic friction between the sled and the ice is 0.10? Now notice the initial velocity is given, the mass is given, and you also have the coefficient of friction, which is 0.10. So let's start with the initial problem here. Notice that why does the sled stop? Because when it is pushed with an initial velocity, there is a kinetic energy, so there is an amount of kinetic force that is being acted on it. But notice that the force and the displacement are in opposite directions to each other, so theta here equals 180 degrees. So remember that part. Now let's write down the given data. So mass is 10 kilograms. You have the coefficient of friction, kinetic friction, which is 0.10, and you also have the initial speed vi, which is 2.2 meter per second. So notice that the sled starts at here and does come to an end point. So let's consider that 2 points as A and B. So we are finally trying to find this displacement d here. So we are trying to find this displacement d while there is a force Fk that is being acted in the opposite direction. Now let's try to find the actual force acting on the object. So work done here is again Fd cos theta So the force that is being acted upon is the kinetic friction, so which is Fk times d displacement times cos theta. Now we have to know the kinetic friction is given, but we do not know the actual value of kinetic friction. So from the original formula for kinetic friction, we can write that kinetic friction is equal to mu k times Fn, which is the normal force. Notice that the sled is having a certain mass, so we need Fg here. So Fg is mg, so m is 10 times 9.81, so which is 98.1 Newton. So now notice that this is the sled. So because there is a g downward, so the normal force Fn is upward, and there is no other normal force being acted, so we can write that Fg equals Fn from this, because there is no vertical displacement and there is no vertical net force. So from this we can write that Fn is 98.1, so Fk can be written as 0.10 times 98.1, so which becomes 9.81 Newton. So we have Fk, so Fk is 9.81 times the d here, so notice that this is d times cos theta, so theta here is 180 degrees. So this is the net force. But we also know from the work kinetic energy theorem that the net force is the change in kinetic energy, so which is the final kinetic energy minus the initial kinetic energy. So it's given that the initial velocity is 2.2 meters per second, while the final velocity is 0, because it does come to a stop at the end point. So this KEF becomes 0. So W net equals minus KEI, so it becomes minus half MVI square. Now the net force here can be written as 9.81 times d cos 180 degrees. So that equals minus half. M here is 10 times Vi is given as 2.2 square. So from this d can be written as minus half times 10 times 2.2 square by 9.81 times cos 180 degrees. Cos 180 degrees is negative 1. So from this we can write that the negative and negative get cancelled. So half of 10 is 5 times 2.2 square by 9.81. So the final answer for this displacement would be 2.5 meters. So this will be 2.5 meters. So this is the total displacement. Notice that we have taken the original definition of work and we have equated it with the work energy theorem to determine the final displacement of the object. So this is how we solve the problem. So next, let's get into the next forms of energy, the next form of energy, which is potential energy. So potential energy, the term potential comes from the fact that this is the energy associated with the object's position, shape, condition, or the condition. Now, there are two main types that we are going to discuss. First is the gravitational potential energy. So it is the potential energy stored in the gravitational fields of the interacting objects. Now, gravitational potential energy depends on the height from a zero level. So it's written as PEG equals mgh, where m is the mass, g is the acceleration due to gravity, and h here is the height. So now, because potential energy is the energy due to the position, so the higher the object, the more the kinetic energy. So here, P in 1, so let's consider that this is PE2. So here we can say that PE1 is greater than PE2. The main reason is because H1 is greater than H2. So notice that the height at which this is there from the ground level is generally higher. Next type of potential energy we're going to talk about is the elastic potential energy. So elastic potential energy is the energy available for use when you have a deformed elastic object that returns to its original configuration. So this is given by the formula PE elastic equals half times kx square. So where k is called as the spring constant and x here is the distance compressed or stretched. So remember that this basically x represents the displacement here. Now the symbol K is called as the spring constant, and it is generally a parameter that measures the spring resistance to being compressed or stretched. So where does elastic energy come from? So elastic energy is stored in the form of the compression or extension. So the amount of distance being compressed is generally considered x here. The distance that is being compressed with respect to the relaxed length is taken as x here, and each spring generally will have its own spring constant based on the size and shape of the material, and using those two quantities we can always calculate the elastic potential energy. So let's try to solve a problem here. So a 70 kg stuntman is attached to a bungee cord with an unstretched length of 15 meters. He jumps off a bridge spanning a river from a height of 50 meters. When he finally stops, the cord has stretched a length of 44 meters. So treat the stuntman as a point mass and disregard the weight on the bungee cord. Assuming the spring constant of the bungee cord is 71.8 Newton per meter, what is the total potential energy relative to the water when the man stops falling? So now we have to calculate the total potential energy. So let's consider that this is the place where he has started from. So this is the part where he has started from. Now let's consider the relaxed length of the bungee cord. So the relaxed length is 15 meters while the stretched length is 44 meters. So the relaxed length is 15 meters and this length is 44 meters. So notice that this is the ground here. So this is the ground here, and this ground is at a height of 50 meters. So this length here is 50 meters. So this is his final position. Now remember that the total potential energy here, there are two potential energies, because from the surface of the earth he is at a height of, notice that this is 50, this is 44, so which means that this distance becomes 6 meters. So he's at a height of 6 meters, and he has also collected, because he has taken a length of 15 meters and stretched it over 44 meters, he also has elastic energy. So he has gravitational energy plus elastic energy. So gravitational energy is mgh plus elastic energy is half kx square. So from the data here, what is given here? So a 70 kg stuntman, and he is taking from a river of 50 meters, and at last the spring constant is given as 71 meters. Now the height here becomes 50 minus 44, so which is 6 meters. The x, which is the stretched length, so this is the stretched length minus the relaxed length, which is 15 meters. So 44 minus 15, so which gives you a total length of 29 meters. Now we have the height, we have the displacement now. So m is given as 70 kilograms. So because this is the strength, so 70 times 9.81 times the height is 6 plus half times k. K is given here in the problem as 71.8 Newton per meter. So k is 71.8 Newton per meter. So 71.8 times x here is going to be 29 square. So when you solve the entire value, it becomes 34,300 joules. So this is the total kinetic energy, and it can also be written as 34.3 kilojoule. So this is the total potential energy. Remember that the total potential energy considers every single potential energy that the object has. So that is about potential energy. Next, let's enter into the topic of conservation of energy. So in this, we are going to try to identify situations in which conservation of mechanical energy is valid. Second, to recognize the forms that where the conserved energy can take. And finally, solve problems using conservation of mechanical energy. So let's enter into conserved quantity. So what do we mean by the term conserved? So whenever we say the term conserved, it means that it remains constant. So this is really important to remember, that whenever you see the term conserved, you have to remember that it means that it remains constant. So let's start with mechanical energy. What is mechanical energy? So mechanical energy is the sum of kinetic energy and all forms of potential energy associated with an object or group of objects. So ME is KE plus sigma of PE. So where kinetic energy plus all forms of potential energy. Now, always remember that the mechanical energy is generally conserved, so which means that the initial mechanical energy is always equal to the final mechanical energy. So this brings us to the conservation of mechanical energy. What does it mean? Is that whenever, so conservation of mechanical energy states that the mechanical energy is neither destroyed nor created, rather transformed from one form of energy into another form. So let's take an example of a pendulum. So let's take an example of a pendulum in three situations where you have swung it. Now, at this position, the pendulum has both potential energy and kinetic energy. Now, what happens at this position, because it is swung up, the total kinetic energy becomes zero, but the potential energy will increase. So what is happening here is that the kinetic energy that was present here is getting converted into potential energy. Here also the same thing. The potential energy increases. The main reason is because the kinetic energy becomes potential energy. Notice that at this point the body comes to rest. So which means that at that point there is a change in the kinetic energy, so which brings the kinetic energy to zero. So thereby converting all kinetic energy into potential energy. So this is how transformation of energy occurs, and this here is the mechanical basis of conservation of mechanical energy. Remember that we always consider this in the absence of friction. So this is one of the important parts to remember. So because friction is what we call as a non-conservative force, so that is something we generally neglect in ideal situations. Let's take an example problem. So starting from rest, a child zooms down a frictionless slide from an initial height of 3 meters. What is her speed at the bottom of the slide? Assume that she has a mass of 25 kilograms. Now, so what is given here in the data? So the mass is 25 kilograms and she starts from a height of 3 meters. Now, so what is happening here? Let's take the slide into consideration here. So let's say that this is the slide where the child comes down. So let's say this is the slide. So the slide has an initial height of 3 meters. So this height here is 3 meters. Now this is position A and this is the final position B. Now notice that here the person has started with zero velocity, so which means that there is only potential energy. At the end, because the potential energy, because the height is 0 meters, so this becomes into kinetic energy. So here at this point kinetic energy becomes 0, at this point potential energy becomes 0. So let's consider this is the initial one and this is the final one. So we know that the initial mechanical energy is equal to the final mechanical energy. So we can write that this as Pi plus Kei equals Pef plus Kef. Substituting the values, we get Pi equals Kef. So Pi here is mgh equals Kef is half mv square. Now she starts from a height of 3 meters and they're asking us to calculate the velocity. So this is the velocity, the final velocity. So from this the final velocity square becomes 2 mgh by m. So mm get cancelled. So Vf becomes square root of 2gh. So that becomes square root of 2 times 9.81 times height is 3 meters. So use a calculator and try to find the value. So 2 times 9.81 times 3 is 58.86 and the square root of that value is 7.67 meter per second square. So this is Vf, the final velocity or the speed at which the kid comes down to the ground. Remember, this is the main way we generally use the conditions to manipulate and solve the problem. So with that, we completed the talk on conservation of mechanical energy. Now, mechanical energy is not conserved provided when you have the presence of friction. So let's take an example. If you have a sanding block slides on a piece of wood, it creates heat. So which means that this heat is dissipated into the block and the surface, which means that we are losing some energy. So we call these types of we call these types of forces non-conservative energy or the non-conservative work. This non-conservative work is generally something we add to the conservation of energy. So when we write the total work done, so this is one of the ones that we add to it so that we consider the heat as well. So next, let's get into the final topic on power. So the objectives here are to relate the concepts of energy, time and power, calculate the power in two different ways, and explain the effect of machines on work and power. Let's start with power. So power is the quantity that measures the rate at which the work is done or energy is being transferred. So power is W over time or energy over time. So an alternative equation for power can be derived from work. So we know that work is force times displacement. So when you substitute it into this quantity here, power becomes force times displacement by time. So displacement by time becomes velocity. So we can write P is equal to Fv or force times speed. So these are the two formulas that we generally use to calculate power. So with that, we end the topic on power and we end the topic on work and energy. So that is the conclusion of module 5. I will see you again in the next lecture.